And this week's lecture is on multiplication. So we did addition, then subtraction, we'll move to multiplication, and next week will be division. In multiplication, we're going to be looking at these particular topics. And then the Common Core standards tell us that we are going to do multiplication of whole numbers in the 3rd grade, and we're going to continue to intensify the problems in both 4th and 5th grade. As always, we start with a set of problems, and we're going to look at how each of these problems represents multiplication, and they each represent a different kind of multiplication. So if we are to look at the first problem with the candy, one piece of candy costs 4 cents. How much would 3 pieces cost? We can just take that 4 cents and just make 3 groups of those and treat that as repeated addition, which is the fundamental concept of multiplication. In problem 2, if Jackie is to walk 4 miles per hour for 3 hours, well, what she is doing is after an hour she's walked 4 miles, after 2 hours she has walked 8, and then 12. So we can say that it's kind of a form of repeated addition as well. Now on problem 3, that is a little bit different. We can represent this with a diagram, as we always like to do with visuals. Notice how the visuals are what cue us in as to what it is we're talking about. So if I were to talk about a piece of carpet that was 3 foot by 4 foot and count out those blocks, I would see that that was 12 foot squared. For the 4th problem, that problem is a little trickier, and that problem involves an array. So if I were to look at that problem as, now I want to note, let's see, what was it? She had blouses and skirts, and so 4 blouses and 3 skirts. So I can see the B represents her blouses, the S represents her skirts. So skirt number 1 will go with each of the blouses. Skirt number 2 will also go with each of the blouses. And if I were to count those things, I would see that there are 12 different combinations. So if I laid those out on the bed and counted them, I would find 12 different combinations of that. Now that is a more complex concept of multiplication. Just bringing this all together, you will see once again we have the part and the whole, and this is this repeated addition, same kind of concept. So we keep moving forward using the same manipulative so that we can solidify what it is that we're learning. We don't have to learn a whole new kind of manipulative. This is a mathematical definition of multiplication where it's n times a, and we see that it's also this repeated addition that is more or less our definition, and then we define multiplier, product, factors. This is a visual for this concept of repeated addition in a more general term. Here are a couple of different ways to look at that area model for multiplication. You can represent multiplication in either of these forms, and it's always a good idea to give all of those different problem types to your students. Alright, now this is a crazy slide, but what it is a formal definition of my product model or multiplication and what multiplication actually means. A little easier way to look at this is with our skirts and blouses, and what we were looking at before with that Cartesian product model was the general. This is specific to my 4 skirts, no, it's 3 skirts and 4 blouses, so that's specific to that. But we could represent that with any number of elements A and any number of elements B, which in turn is a more general form to represent this Cartesian product model. And here is the formal mathematical notation. Not that you will be using this to show your students, but it's just valid that you get to see what the formal representation mathematically is. And driving this point home again about repeated addition, we have the number line represented. I believe this one was shown, something similar to this was shown earlier. So we have a zero property for multiplication, of course. Zero of anything is zero, and if you think about repeated addition as zero groups of 3 is still zero, that is a way to talk about the zero property. The identity property is, the identity for multiplication is 1, so that means one group of something is still however many is there. Moving on to the commutative property, multiplication follows commutative property. 3 times 4 is the same as 4 times 3. Also following the associative property, multiplication follows that as well. Additionally, we have a new property. We have the distributive property, and this is a good representation of the distributive property in a specific form. How many cans of soda are in 3 24 can cases? So you could just say that's 24 and 24 and 24. Or we can look at a new problem, and let's look at this one. We could, in a new way, we can represent this as, here's my 3 groups of 24. We could say that that is 6 of my 10s, and then counting the ones, that would be 12 ones. And in this way we can show the distributive property. So let's represent that. We took the 3 groups of 24, which is 3 groups of 20 plus 4, and said 3 times 20 is 60. There's my 6 groups of 10 plus my 12. Some people might look at this as 25 take away 3. That's another way to look at it. I would say probably this top way would be most common, but you know, we need to teach to all different groups, and just because someone doesn't look at it the way we do doesn't mean that they're wrong. It just means they're looking at it in a different way. And as a math teacher, you need to try to figure out all different ways so that you can speak to all of your students and not just those that think like you. So here is that distributive property over subtraction written out formally. When adding, we don't really have to worry about units, because we can only add apples and apples and oranges and oranges. Here, units change, such as whenever we were talking about the person that was walking, is a very clear person that was walking 4 miles per hour, and you multiply that by 3 hours, the hours would cancel, telling me that I went 12 miles. Here's the others listed in terms of the units changing as well, but I think that second one is the easiest one to look at. Now here are my multiplication facts. Whenever you are showing your students your multiplication facts, try to show them all the patterns and get them to even discover the patterns, which is more important because discovery is the best learning tool there is. Ask them, can they find a pattern along diagonals? Can they find patterns up and down? Can they find patterns across? What else do they see? And you might write those patterns on the board that students see, because finding patterns is truly important in mathematics. Now this would be a higher level pattern, but let's look at this one. If a student said, hey, I see that every odd number is totally surrounded by even numbers. Why is that? But I can look at the even numbers and they're not totally surrounded by odds. And then have a discussion. And even if you don't know the answer, sometimes your students will figure it out, and that's always a beautiful thing. You don't have to be the giver of all information. It's always exciting to me when a student comes up with something that I really didn't see or didn't notice, and then just Just say, well, I wonder why that is, and then you'll have students really get excited about saying why that is. So let's look at that. Every odd number, so let's go and find an odd number. This 15, if I look all the way around him, he is surrounded by all even numbers. If I find another odd number, say this 21, he is all surrounded by all even numbers. And try to figure out why that would be. So now we're going to get into multiplication with larger numbers, and we really need students to understand that it's not a procedure that we're doing. There is, I mean, we can memorize the procedure because that makes it easier, but in learning it we need to look at the manipulatives and figure out what's going on, and then use a procedure to say, hey, we can do it this way, and it would be easy if we could. That way we don't have to do the manipulatives every time. Well, we were looking at 23 times 12, and so we could look at 12 23s and try to figure out exactly what it is that we've got, because if we have 12 23s, we have 12 of these 10s, and then, but since there's a 2 in the 10s place, there's 12 of these 10s, and then 12 of these 10s because there's 2 groups of those. And then I have, let's see, with the 1s, for each one of those, I have 12 of these 3s. And then figure out, well, how is it that I multiply this? How many is it that I have? Because now once I've done that, then I'm just basically adding. So in looking at it in this format, I see that I have 23 times my 10s, and then I have 2 groups over here in the 1s that make up a 10, and then counting my ones that I have left over. In this one I have 12 10s sitting like this, and then 3 groups of my 12, and then here's yet another way to break up that array, all arriving at the same answer of 276. Showing all 3 of those ways with manipulatives is very important. Oh my goodness, 34 times 56. I'm not going to count all of those things. Who wants to count all those things? But I do like it when it's broken apart and I can count by 10s or something of that sort. And then I can start breaking that. This I wouldn't mind circling and looking at what's going on here. And this is just talking about who wants to multiply and add all of these things up. We need to come up with an easier way, and that's what you should, I think that's what maybe you should do whenever you're talking to your students about double-digit multiplication. Try to do it these hard ways and say to them, can't we come up with an easier way, because this is the pain, and then almost let them discover how double-digit multiplication works. It's very powerful. And sometimes I even like to tell my students, we could come up with a way to cheat this so we didn't have to do all of this work all of the time. That would be awesome. And let them believe that double-digit multiplication and its procedure is a way to cheat the system. And some students actually really get into that. So here we are basically using the manipulatives to figure out what's going on. You can use that virtual tool that I like to use from Utah State University in laying those blocks down. You'll see that method in my videos whenever I'm showing you how to do different bases so that you can fully grasp. We do the different bases so that you can see what it's like as a student learning something for the first time, because you can't really understand what it's like learning this for the first time because you did it so long ago. It's now automatic. So here's another strategy. They're telling you to draw lines after every one so that you can show students what's going on. Very nice and easy to do if you use a virtual manipulative and you have a smart board. It's a beautiful way to do it. ask students to find the new groups, ask them do they want the groups be broken down into the large squares or flats, and how do they want to count them. Because looking at this is so much easier than looking at that multitude of blocks that we saw at the very beginning. Here's another strategy broken apart so you don't see all the individual flats. This would be much easier to draw just by hand on the board. And using that method, we could just find the area of each of those 4 regions and then just add. And here's a formal way to take that one strategy and move it to our procedural rules for multiplying double digits. And that procedure is, another word for procedure is algorithm. That's the fancy word that we like to use in this class for procedure. It's algorithm. There's your standard algorithm here moving forward. And here's an array model for multiplying 47 times 24. Let's see what's going on with this and then try to figure out how it works. What you would do is take the 7 times the 2 and put it in your first block. 7 times the 4, put a 28 here. Remember, our 10s are always up on top. 4 times the 2 is a 0, 8. 4 times the 4 is a 1, 6. And just adding as we go across, remembering to carry. So I put my 8 here. I would then add 4, 2, and 6 and get 12. So I put my 2 here, carry my 1, then just add everything in that diagonal, and then my answer would end up being the 1128. Okay, I guess it's kind of important sometimes that you see how I make these things. So I just created this shape using just some general lines and shapes that are there, and I figure I'll do that one there, and then I'll take this one and move it here. I've got to create another one of those boxes, so this one will have to be bigger. So what I'll do is I'll cheat and use this one. I'll Control C and then I'll Control V, and then I'll make that box even bigger in just a second here using more lines. Oops, first off I have to flatten all, otherwise it keeps it as a unit, and because I need to do the 34 times the 31, I'll need another set of those boxes. So I'll need one that goes up. That's not how I'm going to make it. Hold on, I'll figure out another way. Oh yeah, I'm just going to make another square, and then that looks good. And then I'll draw some lines straight down from there and then extend those diagonals. Alright, that'll work for me. Now, we've played this game before, so let me write in what I'm going to need. I'll use the red, and I want 32 times 3. So I'm going to do 2 times 3, which is 6, but in base 5 that's represented as 1, 1. Then I want 3 times 3, which is 9, and in base 5 9 is represented as 1, 4. So adding 1, 4 and 1 are 5, but in base 5 that's 0, carry my 1, and then that would be a 2. So this answer would be 2, 0, 1, base 5. Then I've got 34 times 31. So here we go, 4 times 3, that's a 12, but a 12 in base 5 is 2, 2. And you might want to list your base 5 facts out if you aren't following that. Just list out your base 5 facts. Oops, I got to flatten it because it's getting ready to list out your base 5 facts if you need to, so that you can remember, just like I did in the video prior. And 4 times 1 would be 0, 4. 3 times 1 is 0, 3. 3 times 3 is a 9, but in base 5 a 9 is represented as 1, 4. So let's see what we've got here. Adding, this is a 4, 3 and 2 are 5, that's a 0, 1 in base 5, 6, 7. 7 is a 2, 1 in base 5 and 1 in 1 are 2. So this number would be equal to, I'll write it down here, 2204 base 5. So that's multiplying in base 5, and we can multiply it in all of the other bases, but it's really important to watch this lattice method in other bases and see how you could transpose that to base 10. Now in this next problem, I want you to understand that what you're going to be doing is not just telling students how to do these problems, you have to tell them why their mistake is in error, and not just say nope, that's wrong, but to explain how, oh, I see how you could do that. No, what you're misunderstanding is this. So if a third grade child multiplies 49 times 2 and gets 108, try to figure out what it is that they might be doing. Looking at the 4 and the 9 and the 2 and figure out how in the world did they get 108 is your first issue that you've got to figure out. Then after you figure out how they got the 108, then you have to figure out, well, how do I correct their error in thinking. Alright, so this is what I believe that the student did, and that's going to be half of your battle, is trying to figure out what they did wrong. It took me a little bit to figure this out. What in the world could they have done wrong? And this is what I believe that they did. And of course I put a slash through it and made a circle so that you would know that this is wrong. But what they did was they said 9 times 2 is 18, carried their 1, and then said 4 plus 1 is 5, and then carried on from there. So what you're going to have to do is show them exactly why this is wrong. So figuring out how they did their problem wrong is your first issue, and then once you figure out what they did, trying to explain how what they did was wrong, and not just show them again the right way to do it, because that doesn't help them really. And that's our lesson for this week. Your job is going to be tough. Not only do you have to explain how to do the problems and thoroughly understand how to do the problems, you have to figure out how somebody can make mistakes, and then you have to fix those mistakes. It's an awful lot of fun, though.